In this video, we're going to look at how you calculate a bond length from XYZ coordinates. So we're going to start looking into molecular structure, specifically looking at XYZ coordinates of molecules, and then figuring out how we determine things like the various internal degrees of freedom from them, things like bond lengths, bond angles, torsion angles, etc. So starting off with the simplest case, we're going to look at bond lengths. So I've got the equivalent of an XYZ file here for an HF, a hydrogen fluoride molecule. If I wanted it to be a real XYZ file, I'd need a line above it with the number 2, then a comment line, then these two lines. But we can see we have XYZ coordinates here, usually in units of angstroms. And I have this molecule open in Avogadro. We can see pretty simple molecule, not a lot going on there. And if I go to the extensions tab and go to something like, say, Psi4, you can see that verify for yourself that these are indeed the exact coordinates that I have written down in the file here. Okay, so how do we calculate this bond length for this molecule, which if I go to this measurement tool, Avogadro claims to be 0.939 angstroms. Okay, how do we arrive at that value? All right, so we know that our nuclei are represented as fixed 3D Cartesian points here in an XYZ file. So what we need to do is find the distance between 2 points. So how do we generally find the distance between 2 points in a Cartesian system? So distance between 2 points, we're going to use the Pythagorean theorem. So that's going to allow us to calculate this distance, our RFH, between the fluorine and the hydrogen. Okay, so to start off, let's look in the XY plane. So we've got, for example, a point here in the XY plane and a point here. So this might be for our fluorine, and that's a point x1, y1. For our H, that might be x2, y2, being the first and second atoms respectively, so H and F. All right, so we are going to connect the line between those two, and then drop down on our axes and create a right triangle with a hypotenuse. Okay, so we have two values here. We have delta x and we have delta y. So delta x equals x2 minus x1, absolute value. Delta y equals y2 minus y1, absolute value. And then we've got a hypotenuse here, which is some distance. So this hypotenuse is, from the Pythagorean theorem, going to be equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. Okay, now we can repeat the same thing in 3 dimensions. Since we have this hypotenuse there, now we can project that out of the board, going out of the xy plane into including the z coordinate as well. So we can do the same kind of thing, where now we're going to have, instead of this being our hypotenuse, this is going to be our bottom axis here. So now our distance along the hypotenuse is going to be r. It's going to be RFH. This distance down here is our question mark, which we defined there. And then we have the actual points. So we have x1, y1, z1, and x2, y2, z2. So this height here on our triangle is delta z, which equals absolute value of z2 minus z1. So now if we do Pythagorean theorem of these, we're going to have y2 minus y1 squared plus x2 minus x1 squared square root, and then that's going to be squared again, so the square root's going to go away. And we're going to have that plus absolute value of z2 minus z1 squared as well, then square root of the whole thing. So what ends up happening is our total distance for two given points here, rij, if we generalize these 2 and 1 to general numbers I and j now, between atom I and j, is square root of x2, or xj, if I'm going to be using the letters here, xj minus xi squared plus yj minus yi squared plus zj minus zi squared. In this case where we have j being 2 and I being 1. Okay, so that is our final answer for what the bond length is for the general formula. So now we're going to take note of a few general properties of what these values can be. So in general, we're going to have 0, which is less than or equal to rij, and hopefully it will be greater than 0 unless I equals j. And so 0 is less than or equal to rij, which is less than infinity, as long as these are all finite values in the XYZ file. Okay, so on to calculating it for this specific case of our fluorine and our hydrogen. We said from Avogadro that it's 0.939 angstroms. So let's go ahead and calculate that. So we have RFH equals big parentheses there. We're going to have xj for 2 being 0.64417 minus negative 0.29502, and then close parentheses, square that. And we could just stop right there because the other two are the same, so delta y and delta z are both 0. But let's just write them down for good measure. So plus 0.75280 minus 0.75280, the first and second values being those and that respectively, squared plus final line is just 0.00000, that value, minus this value, 0.00000. Okay, squared, and close our brace and take the square root. Okay, so what does this value end up being? So that gives us RFH equals, okay, we're going to have the distance between these two is 0.93919 squared plus this difference squared is 0.0 squared plus this difference squared is 0.0 squared. Then we take the square root. So as you can see, this distance being 0.939, we're going to square that, add 0 to it, and take the square root. So that's just going to give us the same value that we ended up with before. RFH equals 0.939 angstroms. So we've confirmed that we have the correct formula, and this is indeed the same formula that Avogadro was using when Avogadro computed that value in our earlier demo.